Hi, Missy. Okay, I'm going to try to run through my EEL derivation. I'm going to try to do it thoroughly, but as quickly as possible so you don't have to watch this terribly long. So I'll talk to the kids. We need an equation for EEL. We've derived some. We've done it by experimentation on others. Which way do you want to do it? Do you want to do a lab? They'll all say no. And I said, all right, we'll derive it. How do we derive the others? EK, and in some cases I showed them EG. Um, it's by how much work we do, right? So the EEL, we need to do work. Now with EK, we did that by exerting the force on the bowling ball. That work went into its kinetic energy. With EG, that work went into changing its height, adding to the gravitational energy. What are we going to do here with EEL? I'll give time to think about that. Some kid will suggest a rubber band or a spring. There's one of those big rubber bands on the mess of a teacher station in 65. I kind of wrap it around a chair and say, okay, so we're going to extend this rubber band. I will pull back on it. I'm doing some work on it. That will increase the EEL of the rubber band. Okay, how much? Well, our work equation is F delta X. So now we have a problem because what we did previously is we had this force with the bowling ball and with my raising an object above the table to change its gravitational energy. This force was constant. And now this force is not constant. Because think about what you need to do with a rubber band or a spring. As you pull it back, to pull it back a little distance requires a very small force, but to pull it back farther requires a bigger and bigger force. So what do you think that graph would look like for a spring? Well, let's go back before we do that and think about what that graph looked like of F versus X for the bowling ball. When I exerted a force on the bowling ball, I exerted a force and it was constant. Okay, what's that going to look like now for the rubber band? And I give them some time to think about this, just a minute or two. Some kids may suggest some sort of curvy thing. A lot of kids will do that. I'll say, okay, great. If it's a curvy thing, it could well be that too. But most typically for most objects, it's this kind of linear relationship. Great, that makes sense. That means the farther back you pull this, the greater the force is needed to pull it over that distance. Marvy, hey, give me the equation of that line. Well, this is going to be F equals blah, 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 some number, the slope, times x, and the y-intercept would be 0 because 0 displacement requires 0 force. What are the units of this? That's going to be newtons per meter. Great, so what does this number tell us about the rubber band? What would happen if I had a different rubber band? I use different colors. This is green, this is red. If that were the graph, this is kind of and they'll come up with this. This is kind of a description of how stiff that rubber band is, although I really try to stay away from that word stiffness or stiff. This is how much it resists being pulled back. And we call this the spring constant. This is how many newtons of force it requires to extend it or compress it by 1 meter. And that just gets this letter K. So I can write F equals Kx. Now here's your point about the springs. What I say is, hey, imagine you have a slinky. Would the spring constant for a slinky be big or small? And I don't actually show them the slinky, although you easily could. And they'll all say, oh, it should be really small because slinkies are easy to compress. Great, fine, or to extend. What object can you think of that would have a really big spring constant? In one class, one kid said an automobile shock in the suspension of a car. In another class, some kid talked about in a gym, great big thick elastic rubber bands. Great. So this is just kind of a measure of how difficult it is to extend or compress that spring. Okay, great. So that's that. Now, what do I do about the fact that this force is changing? It's not constant, so I can't just plug something in here. It's not a constant number. Well, let's think about what we did with the bowling ball and this, well, I guess we can go up here, this fx curve. What did we do? To find the work, we simply multiplied the force that we applied to it and we multiplied it by, and I kind of do this visually and it gives them the idea, we multiplied this force by this distance x, or delta x, that we extended it. And we multiplied this by this to get the work. So what am I really doing here? And in both cases, some kids said you're taking the area under the curve. I'm like, great. So work is not only F delta x, work is area under, and you'll write this legibly, unlike what I'm doing, Fx curve. Oh, well now with EEL I have this problem where that's not a constant, but let's use this idea then and figure out how much work is done by taking the area under this curve. So what is that? So the EEL that the spring gets is equal to the work done, which is equal to the area under this curve, which is 1/2 the force applied times the displacement, or x, how far you pull the spring back. But what is this force? What is the maximum force that I've applied? Well, that comes from this equation that we've talked about, and so that's 1/2 times kx times x, and that is 1/2 kx squared. That is our equation for elastic energy. We now have an equation for that. We have an equation for that. Be sure to tell them what G is. I have this equation. E chem, there is no equation. E therm, there's no equation, yet we'll still sometimes be able to actually calculate these, and we're done. I hope that makes sense. This whole thing took me 25 minutes, 25 minutes or so in class. So hope that helps, and ask me any questions you got in the morning. Bye.